right, hi everybody. Let's jump in to 2.4. Go. So lecture, all right. So we've done the limits introduction, going to the precise definition of a limit. Turns out the way that we thought about limits in that introduction, that's going to be the way that we think about limits through the rest of this chapter in this course. However, we should take a moment and pause and realize that we're actually not being all that precise or all that mathematically precise the way we were thinking about it. This is going to set us up well for things that occur much later, not even in this class, but even in future courses that you take, in calculus courses that you take. With the precise definition of a limit, this one particular section, it really serves those people who are thinking about being math majors or really taking some high-level math courses. For those of you who are not, hey, sorry, you gotta sit in it as well and learn it, because it's good for you too. But you know, it's really for those math majors and for other people who might just take very high-level calculus and higher level math. You need to have seen this right now while we're in this conversation about limits. So sorry if this doesn't apply to every single person as you're going forward. But you know, if you need to take Calc 2 and Calc 3, depending on who your teacher is, they might really lean back heavily on what we're going to see introduced in this section. And you don't want to have missed out on that, or that to be like a new conversation for you, for sure. So it's got the potential to apply to everybody, although this is really geared towards, like I said, those math majors. Okay, let's get into it. Also, you know, I'll tell you, you know, kind of in 2.2 and 2.3, probably, you know, more or less, like things have been going like pretty well. Like it's challenging, it's new, but probably for most people, like it feels pretty doable so far. And then this section comes and you're like, oh my gosh, what is going on? Like my whole world got turned upside down. Well, let's find out what this is all about. The precise definition of a limit. The less precise working definition is as follows. If, as x approaches a, f of x approaches L, then we can say that the limit of f of x as x approaches a equals L. That L is the answer to our limit question. Why is this not precise? It's because of that word approach or approaches, the very word which makes a limit what it is, right? It doesn't matter what's happening at the value itself. It matters what's happening as we are approaching that value, as x approaches a, as f of x approaches L. But what do we really mean when we say approach? And how close do you have to be to a number to be approaching it? We ran into this problem when we were doing tables in the previous couple of sections, right? When you make a table and you try and get the answer to a limit with a table, you're like, well, how close do I need to be to really know for sure? And you can't, right? So this it all kind of ties. Okay, it's been hinted at. So let's look at this specific example. We're actually going to stay with this simple example for a while, just to kind of build the foundation that we need in order to get to the precise definition at the very end of this discussion. So let's look at the limit of 4x minus 1 as x approaches 2. And we can realize pretty fast that the answer to that is 7, right? All we'd have to do is plug 2 in. So the issue is not getting the answer, but we're gonna like explore this like, you know, pretty deep. It says as x approaches 2, 4x minus 1 approaches 7. Okay, sure, yeah, definitely. But how close must values be to approach, right? Like in quotes. The word approach is not a very mathematical word. It's not well defined. You could argue, well, you can never really approach because you have to get infinitely close, to approach something. Here's what we'll do instead. We'll make this precise. By precise, we mean we're going to give it values, specific values. We need specific distances from 2 and from 7 to be precise. What does that mean? How close? Let's rephrase the question just a little bit. How close must x be to 2 so that 4x minus 1 is within 0.1 of 7? Let's say all our aim is to get our function 4x minus 1 within 0.1 of 7. Okay, that would be precise. Right now, once we're within 0.1, we've accomplished our goal, and we're good. How close do we have to be to 2? We know that 2, right? We plug in would equal 7. So like, what's kind of like the window of error, almost like how close do we have to be to the 2 so that we get within a certain error of the 7, within 0.1? There's a couple ways we go about this. The simplest, we're gonna see a couple of ways. The simplest would be say, hey, let's take 4x minus 1, and let's say it's greater than and it's less than, like the extremes. So if we're getting within 0.1 of 7, then it would have to be somewhere between 6.9 and 7.1. And if we can make that happen, so well, all we need to do here is isolate x in the middle, and then x will be between two values, and we'll know how close we need to be. Okay, so if we solve this, we isolate x in the middle. Since we have this 3-level inequality, we can add 1 to each of the 3. Okay, so now 7.9 is less than 4x is less than 8.1. And we can divide them all by 4 and check it out. We realize that x has to be between 1.975 and 2.025. Okay, interesting. If x falls within that little window, then 4x minus 1 is going to fall within this window. And that's what we're looking for. X must be, if you kind of think about that, well, how close to 2 does x need to be to fall within there? X needs to be within 0.025 of 2. It could be, up to that large in either direction, above 2 or below 2, 0.025. All right, doesn't seem so bad. Let's take a look at that in a drawing. What would that look like in a drawing? How close must x be to 2 so that 4x minus 1 is within 0.1 of 7? Let's say, all right, there's the graph more or less of y equals 4x minus 1. It's got a y-intercept of -1. It's got a pretty steep slope of 4. Okay, that's basically what it looks like, give or take. And we know it goes through the point at 2, 7. Okay. Within 0.1 of 7. So we're going to draw little lines a little above and a little below the 7 at 6.9 and at 7.1. Okay. So it creates like a little cloud around 7, if you will. It's supposed to be symmetrical. You get the idea. Here's what the answer we just found for the 2, like how close do we have to be to 2? Here's what it would look like graphically. We can extend this line out from 7.1 until it hits. And wherever it hits, we can then drop that straight down to the x-axis. And same thing for 6.9. We can extend that out until it hits and then drop that line straight down like so. And it turns out if we do that at 7.1 and then drop that would cross the x-axis at 2.025, same number we saw a moment ago when we isolated x in the inequality. And 6.9 would land at 1.975. If we were to plug this value in, right, we would get 6.9. If we were to plug that in, we'd get 7.1. So we can tell, hey, if our x value falls within this little window, this little cloud, then our y value is going to fall within this slightly bigger cloud on the y-axis. Okay, well, that's kind of, all right, that's kind of nifty, I guess. Where's this going? How is this leading us to a more precise definition? We're building it. We're getting there. Okay. Here's another way to approach the same question. Still looking at the limit of 4x minus 1 as x approaches 2. We know that's equal to 7. Right? We're going to ask the same question. How close must x be to 2 so that 4x minus 1 is within 0.1 of 7? But notice we set it up very differently. Instead of taking 4x minus 1 and putting it between 6.9 and 7.1, we've done something that looks a lot different. We've got some absolute values. Okay. We're taking our function and we're subtracting what the limit will equal. And we're saying the difference between the function and the y value, what the limit equals, if we find that difference or that distance is going to be less than 0.1. There's a reason behind this. I know this looks really strange. What are we saying here? Wherever the function ends up, whatever its distance is from 7, and maybe this is a little bit above 7 or a little bit below 7, but whatever that difference is, whether this works out to be positive or negative, right? The absolute value should be less than 0.1. If we're going to be within 0.1 of 7, that means the difference between them will be less than 0.1, either positive or negative. We are going to simplify this, and we're going to end up realizing just how close x has to be to 2. And it's pretty cool how this is going to work out. Okay, what are we going to do here? Let's begin just by simplifying what we see inside the absolute values. So I know I have these parentheses here, but they're really not actually doing anything. So let's just go ahead and subtract, right? That's the absolute value of 4x minus 8 is less than 0.1. We can factor out the 4. Because 4 is positive, we can just take it right on out. No problem outside the absolute value. So we got 4 times the absolute value of x minus 2. And then we can divide the 4. And what do you know? The absolute value of x minus 2 is less than 0.025. And so we know that how close must x be to 2? The distance between x and 2 must be less than 0.025. We can stop right here. We're not going to isolate x. We're going to leave it just like this, right? Here we said, what's the distance between our function and 7? Now we're saying, what's the distance between x and 2? Subtract them, throw absolute values on it. That distance, whether x is a little bit too big or a little bit too low, or a little bit larger, a little bit lower than 2, when we subtract them, that absolute value is going to be less than 0.025. We come to the same conclusion. It is in this style that we're going to present the precise definition of the limit. So hence why I do it here with, an easy example, if you will, with this limit. Okay, where is this going? How is this going to be more precise? Okay, we're still looking at the limit as x approaches 2 for 4x minus 1 equals 7. All right. But now let's generalize things. We need variables for the distances. So no longer are we going to say that we're within 0.1 of 7. We're going to use a variable. And no longer are we going to come to the conclusion that we need to be within 0.025 of 2. We're going to use a variable. And it's that variable that's going to make the leap to then give us a precise definition of a limit. We're going to call the distance from L. The distance from L, let me just read it, is known as, that's a Greek letter, epsilon. That's the lowercase epsilon. The distance from A, the A is the where X is approaching, right? The distance from that number is delta. There's a lowercase delta. The uppercase delta is a triangle. Maybe you've seen it, like a frat house or sorority house or something. The lowercase delta kind of looks like a D, right? Kind of script, kind of fancy. Okay, so we're going to look at this absolute value style again. But now we're going to use epsilon. Right before we use 0.1, but now we're making that leap to generalize things, use this variable. Now, what kind of makes this whole idea of the precise definition like just all the more challenging is that we're using, you know, this kind of it's not obscure, it's, you know, but probably not as well known or used Greek letter epsilon. And whenever you use, you know, Greek letters and the more exotic Greek letters, that just makes things seem like they're harder than maybe they would have been otherwise. But you got to learn how to write them. It's like a backwards 3, you know, and that takes some practice, and that makes your brain hurt for a while until you kind of get comfortable with it, you know. And then delta is kind of a funky letter to write, and that all just makes this way more difficult than it needs to be. Well, that's the way it is. Everybody uses epsilon and delta for these, and so get used to it. And it's good. It's good practice. You're getting used to more Greek letters. I'll tell you what, we've been talking for a little while. Let me stop here. We've done a lot. We'll pick it up, continue this conversation in the next video.